Thanks for the introduction. It's my great pleasure to speak here. So I'm gonna tell you, like as the title suggests, like a sort of new invariant called involutive Khovanov homology, and what I mean by it is interestingly trivial. And this is all joint work with Darren Chen based on this archive preprint. So I wanna start with some motivation of this project. Apparently that comes from the involutive Higa floor theory. So remember that if you have a closed three-manifold Y, the first step of defining Higa floor homology is to choose, like, pick some Higa diagram for Y, and then you run some like Lagrangian floor theory package to build up your Higa floor chain complex. I'll just use the simplest like height version and F2 coefficient here for simplicity. And like, so like picking a Higa diagram introduces some like very non-canonical choice, but on the other hand, it also like brings the possibility of having some additional symmetries that you may be able to utilize. So that's the idea of Hendricks and Lesko. So they defined the Higa floor like involutive Higa floor homology by using this conjugation symmetry. So that is like if you have a Higa diagram H, you can consider the conjugate diagram H bar, which is just like you take the opposite orientation of your surface and swap the alpha and the beta curves, and you get another Higa diagram for the same three-manifold Y. And there's a canonical identification between the Higa floor chain groups. Oops. Okay, I'm gonna Higa floor chain groups of H and H bar. And there's another way to relate this to chain groups. That is like H and H bar are related by some sequence of Higa moves. So you can just use a that induces a map like between these two chain groups, and by the naturality of Higa floor homology, by you have Thurston and Zomke, this map is well defined up to chain homotopy. So you can just compose these two maps and get the very famous iota map in Higa floor theory, and that will be a map from CF height of H to itself. And the involutive Higa floor homology is just some invariant you can cook up from the iota complex for this thing. All right, so that is the motivation of this project. We want to kind of mimic this construction in the setup of Khovanov homology. So, but like before talking about involutive Khovanov homology, let me just do a very brief recap on what Khovanov homology is. Like I'm sure most of you know what that is, but so like if you're starting from a K, link K, then the first step of defining that is like you also need to pick some very non-canonical choice, that is the link diagram D for this link. And like after that, you run this usual process. You take a cube of resolutions and apply some Khovanov TQFT, and then you get the Khovanov chain complex, denote this by CKH of D. And so like it's an invariant of K up to homotopy, and it's bi-graded with the homological grading coming from the cube of resolutions, which is basically like sum of the like resolutions and up to some constant. That will be useful later. And there's another quantum grading. And it is natural in certain sense, like if you have two diagrams for this node K, and you have two models of this Khovanov chain complex. But like after picking some like isotopy or like equivalence class of Redmaster moves, you can have some well-defined chain equivalence between these two chain groups. And if you do slightly more work, that gives you the cobordism maps in Khovanov homology. That is many people's work. And the last thing I want to mention is that it allows some like tangle invariant due to Khovanov and Banatan independently. And that is, well, that basically allows you to do the computation at a very local level and then just glue them back to get the desired result at the level of link homology. All right, so we are not ready to define these involutive Khovanov things. So the first question, like you might ask, is like which kind of symmetry you're gonna use to develop this theory. So the answer is we're gonna use this flip symmetry. That is like so if you have a null diagram D, the flip diagram is another diagram. I'll denote this by D star. That is essentially given by if you have a null K in R3 and you have a projection plane, then what you do is like you pick an axis on the plane and you rotate this node about this axis by half around, and you get another node that is isotopic to it, and you project it to the same plane. And if you prefer a 2D picture, that is what it does. So you have a node diagram, and you just take the mirror of the diagram and then change all the crossings. So hopefully that this picture can convince you that like this node diagram and its flip diagram are not necessarily the same. So I was intentionally drawing this like trifold with a long tail, like so like this one and the flip diagram are not like strictly the same, and they are kind of the same. Reflect the fact that like the trifold is strongly invertible, and this diagram is transvergent, and we'll get back to that later. And so like you have some maps between the Khovanov chain group between for T and T star that is just a canonical identification. And another map you can get is that like for these two diagrams, like you have some preferred isotopy between them, basically just given by you rotate it half around, and you get some like by this naturality stuff, you get this R map which is well defined up to homotopy. And if you compose these two maps, you get the kappa map, which is just an analog of the E-eta map in involutive Higa-Floor theory, and it is just the composition of eta and R. And we just define the involutive Khovanov homology using exactly the same formula as the involutive Higa-Floor homology. Maybe like here's cohomology, but it doesn't matter. And it's pretty easy to prove like this one is indeed an invariant of K, just doing some homological algebra. And like as the title suggests, like this invariant is not very interesting. So the result we really prove is that this kappa map, like as an analog of the iota map, is chain homotopy to the identity. So it doesn't give you any new information about the node K. So the corollary is that this involutive Khovanov thing is just two copies of the ordinary Khovanov homology. So that's pretty sad. Oh, I want to mention like so this version of like involutive Khovanov homology we define is using this intrinsic symmetry. There's another version of involutive Khovanov homology defined by Taketo Sano. He used the external symmetry for its strongly invertible node, and I'm not making any claim about his invariant is true. All right, so that is our definition of that's the main theorem, and in the remaining time I will going to explain the idea of the proof of this thing.
Can you say again, what is the definition? It's the cone of what?
It's the cone of Q times 1 plus kappa, where kappa is the map defined like above. So Q is just some formal variable that squares to 0. What is F? Sorry, which F? The field F. F2. Yeah, I forgot to say, like, I'll just work over F2 for the whole talk. Yes. Any other questions? Cool. All right. So, well, so to prove this theorem, like, let's get back to the definition of kappa. So it is a composition of two maps, but one of them is like fairly easy to understand. The eta map is just like, you know, you're basically doing nothing. And the R map is pretty hard because like it involves some like unspecified cobordism that you need to write down an explicit Redmaster moves to really compute it. So that's the idea of, that's the observation here. So we want to have some sequence of Redmaster moves that can really compute this, this half around map. So here's the idea. So if you have a braid, K-strand braid beta, then if you wanna like flip it across the y-axis, then what you need to do is just you conjugate that braid by the half twist. So this one may not be very intuitive, but here's a better picture maybe. Like imagine like you have some like heavy like industrial container, like you wanna, and for some reason you wanna like move it move it to another direction. Then what you can do is like you can put some like arrow chains like on the top and on the bottom and try to like drag it very hard. And then like hopefully you can get to this like this curve in another like direction. So that is like the usefulness of math in real life. You know? Yeah, and so let's get to math. By using this idea, let's first present our node K as a blood closure of some braid. So here I have like n crossings that like are separate in n layers. So like each of them is just like an elementary grid with a single crossing, and you like close them up by some cups and cups. And the first step is to introduce some pairs of half twists and their inverses. And this is just literally doing nothing. You like insert the like between each layers. And the next step is to apply this observation above to flip each level of the tangle to its like to the ordinary tangle. And so after that, most of the half twists we just introduced are eliminated. But there are two left on the top and on the bottom. Then what we do in the next step is to just like use this this kind of like isotopy to eliminate the remaining two half twists. And now you get back to the ordinary diagram. So that gives you a sequence of like explicit sequence of Randmaster moves that you can compute this like flip map. Any questions about this? So the idea is quite simple. You just like do this industrial thing. Okay, cool. So like that gives you some sequence of Randmaster moves, but like in practice you wanna compute it. So it's still pretty hard, especially for the second step, because like if you look at it further, like it involves like so first like a half twist. If you have 100 like 1,000 strands of like braid, then the half twist has like millions of crossings. So that's pretty hard to handle. But so we need to look at this picture like closer. And so let's look at the second step of this this process, just at a very local level. So what we have like locally is that like we have some like conjugated flip of Ti, which is just a single like elementary braid, and we want to use some sequence of Randmaster moves to move it back to the original tangle Ti. And so this rho I, like like if you draw it down, like it has like many Randmaster 3 moves and maybe some Randmaster 2 moves that I forgot. But like it is in general pretty hard to compute. So what we do is like the idea is, so like the crossing we really care about is the one in Ti, but not the ones like in the half twist. So why don't we just resolve this crossing? So if you, I'm just drawing one cases, but another one is exactly the same. So if you just resolve one of the crossings, then what you get is like this kind of two-step complexes, and in the middle there is a like crossingless diagram, and the top and the bottom are some braids, some half twists. And so you can see like from this, maybe you can see, but like from this picture, like for this like one resolutions, you have some cobordism map from this to this by just like cup sliding, slide this cup to the bottom, and like you can cancel the half twist out. And in fact, you have some cobordism like that. That is basically you eliminated the this half twist thing. And the important thing here is that this rho I0 and rho I1 maps just have like they are induced by some Randmaster 1 and 2 moves, but not Randmaster 3. So that will be important, because because like there's something called like very strong deformation retract, which allows you to use some homotopy perturbation lemma to really like create this homotopy. But so for now, like you have some diagrams. You have some diagram, and it is just commute up to homotopy. So what you can do is like you just add this homotopy, right? So like now the diagram on the right is just strictly commute. But like there's still question that why, like what is the relation between rho I and this like the sum of this 3 map on the right? And so it turns out that like this map is homotopic to the ordinary map rho I, so you can use it to compute that. So that is like we draw ideas from like McVeigh's paper and Rosansky, like they use the what is called like cup sliding trick to do that. And also need the notion of K-H simple from Bannerton or sweep bimodule from Khovanov to make sure that like essentially the automorphism of this kind of simple modules is also pretty simple. So that is the local picture we had. So the takeaway is we can use this red diagram, which is filtered with respect to this two-step filtration to compute a map on the left. All right. So the next step is like we go back to the global picture. So we can compute the flip map kappa like from this four-step composition. The first step, eta, is just the trivial like canonical identification between the Khovanov complex for D and D star. And the second step, omega, is like is the one corresponding to you introduce some half twists. And rho is corresponding to the one that you're really doing this flip for each tangles. And finally, rho 0 is the one corresponding to like you eliminate the last two half twists. So like they are like the last three steps correspond to the three steps in the red master move picture on the top right. And so now the observation is that like in each step of this complex, we have a 0, 1 to the n grading, which, or I'll call this cubical grading, and that just comes from the ordinary in which way you resolve the ordinary crossings appearing in D, and so like we have a composition of 4 maps, but 3 of them actually preserves this cubical grading. So eta, rho, omega, and rho 0 all preserve this cubical grading because like they're kind of just doing nothing. And the problem is like our map rho, like the most complicated one, does not preserve this like cubical grading. But the only thing we know about like the composition of the whole map is that this kappa map preserves this the homological grading. But like from the local picture we just discussed, we can actually perturb the rho map such that it's going to be filtered with respect to this 0, 1 grading. And like global speaking, like it's like the kappa map can be perturbed to another map kappa prime, which is filtered under this cubical grading. So the idea here is kind of from the work Involutive Boulder floor homology by Ali Shahi Tung Zhang, where they perturb the iota map to make it filter with respect to some similar filtration and use that to build some special sequence for involutive Higa floor homology of branch double covers. So here the idea is kind of the same, but like the next step is the real magic. Like actually like this kappa prime preserves this cubical grading. That is because like it is filtered and it has homological grading 0. So you know like the homological grading is just the kind of the sum of the cubical grading up to some constant. So actually you get a like way more stronger like conclusion. So kappa prime preserves this cubical grading, which means essentially you just need to compute this like for each separate corner, and there's no like interaction between like different corners. So like we just compute this for like at each corner it's just an unlink, so you just compute it and turns out to be literally the identity map. So that finished the proof that like this kappa is actually chain homotopy to the identity. Any question about the proof? Okay, cool. So I'm almost like finished the trivial part. So let me come into the interesting part. So like I've already proved like this kappa is homotopy to identity, and let's restrict ourselves to strongly invertible knot. Remember that if you have such a knot, you have 2 ways to draw that like equivariantly on a plane. One of them is like you can put the axis on the plane and you get the transvergant diagram. This was used by Loeb-Watson and as well as Sano. And another way is that you can put the axis perpendicular to your plane and you get a transvergant diagram. This was used by Lipschitz and Shakar. So like there are two ways of drawing that, and each of these like diagram has a gives you a model of Khovanov chain complex, and this involution gives you this geometric involution gives you a like involution on the chain complex for each like these models of Khovanov chain complex. And like a priori, there's no reason to expect like, well, how would you compare these two involutions? Because like they are even living like on different chain complex. But like after, if you fix isomorphism, like just some arbitrary isomorphism between these two Khovanov chain complexes, as long as it's induced by Radmaster moves, then like the conclusion is that the induced map on Khovanov homology for these two involutions are the same. So this is kind of a direct corollary of our main theorem that is homotopy to the identity, and you apply this like the main result to the transvergent diagram, and you compare that with the introvergent diagram, you get a proof. Now, I also want to mention like this is kind of predicted by the Witten's proposal on, well, you know, to recover Khovanov homology using some gauge theoretic construction. Because if you have such a picture, like both tau t and tau I are induced from this geometric involution, and then there's no reason to say like you have two different involutions from the same construction. So that is like kind of predicted by that, but you know, like our result is you can think of that as a elementary or combinatorial algebraic proof of this prediction. All right, so I'll end up here, and here's the QR code for our paper if you're interested in, and thanks for listening. Yes.
So if you rotate 360 degrees, that's an important ingredient in showing that Khovanov homology is well-defined for links in an unparameterized oriented B3.
Yes.
And I was wondering if your half rotation thing says something about Khovanov homology being well-defined for links in an unparameterized unoriented B3.
Maybe. I haven't thought about that, so sorry. Yeah, that sounds reasonable, but yeah. Thanks for pointing out that. Yeah. Yes. You mean like our version or Taketo's version? So I would say like the previous result about strongly invertible knot is like you have two different types of diagrams, so you can like make some non-trivial claim about that. But for two periodic knot, I don't think like you have like two different types of diagrams, so you can just do this. You only have one way to draw that equivariantly. So yeah. But I think Taketo's paper has some like say something about two periodic knot if you want to look at it. Yeah. Yes.
What is your expectation for arbitrary distribution?
Sorry?
If you work with an arbitrary field.
That's a great question. So like if you work over Z, the problem is that, well, you know, like you have some overall some ambiguities, even though like that can be resolved, but well, so the expectation is that it is so like this. So the expectation is that like this claim still works, but you will not get the identity map in the final, because like for unlinks the result is not the trivial map. And like if you work over like the Banatan deformation, like basically the same, but we don't quite know like what is the result.
Maybe a question. Is it specific to Khovanov, or is it formal? And if you go to GLN homology, you get something similar?
That's also a great question. So we are currently thinking about that. But like there are some like technology different, but I think this idea should work. But like there's some technology that like we need to develop.